Okay, so good morning, everyone. This project was titled Simulating the South African Forestry Supply Chain, as Simon said. It was a cross-faculty collaboration between industrial engineering and forestry and wood science department. Prof. James Backer was a supervisor on industrial engineering side, and Simon was my co-supervisor on the forestry side. So this project was launched after research conducted by the Forestry Department yielded a high-level conceptual map of the South African pulpwood supply chain. This conceptual map identified and strengthened the need for building a computerized simulation model for the South African forestry industry. In 2018, as Simon already mentioned, SAPI and York Timbers agreed to fund this research. And so in 2020, the hard work of mapping out, conceptualizing, and simulating the forestry supply chain began. So the research statement for this project is as follows. The purpose of the study was to provide base simulation models that demonstrate some capabilities of discrete event stochastic simulation when applied to the South African pulp and saw timber supply chains from nursery to mill gate. The simulation models aim to provide support for strategic decision-making by allowing scenario analysis through experimentation and bioobjective optimization. This is an example of a generic forestry supply chain. Note, however, that it is only a very high-level representation of a forestry supply chain. The two supply chains that we simulated in this project were much more detailed than this. But in essence, both the pulpwood and saw timber supply chains start at the nursery gate and end at the mill gate. So just to summarize, this study focused on the pulpwood and saw timber supply chains within the broader South African context, as seen by the stakeholder companies SAPI and York Timber. For the pulpwood supply chain, we simulated eucalyptus, and for the saw timber supply chain, we simulated pine, and also included splitting of products into different product groups from harvesting onwards. So just to give you an overview of where this project fits in, this research project was the first attempt at developing simulation models for the South African forestry industry. The aim of the research was to demonstrate how forestry supply chains can be modeled using discrete event stochastic simulation, and how these simulation models can then be used as a tool to perform strategic supply chain analysis. This research should therefore be seen as a foundation for future research into the South African forestry supply chain domain. The simulation models developed in the study include both the silviculture and logistic parts of the supply chains. In order to understand and map out the supply chains, we conducted several site visits. This is an example of one of the site visits to the SAPI nursery in KZN, which was instrumental in helping me understand the silviculture, the silviculture part of the supply chain. Those are eucalyptus seedlings. The logistic or production part of the supply chain included harvesting, extraction, and transportation. Part of the site visits were targeted at helping me understand the harvesting and extraction process, as well as the loading and transportation of logs to the various sites, such as depots, siding, and mill. On the right is me taking a spin in a harvester, courtesy of Simon. The methodology followed in this project is shown in the slide. Firstly, research was performed in which an in-depth literature study was done. Secondly, process models were developed to understand the structure and complexity of the supply chains. Then concept models were developed for each supply chain. The concept models functioned as the first draft to determine the simulation model logic and required features. Data identification and acquisition was then necessary, followed by model translation into the chosen simulation software. Finally, model verification and validation was done, followed by experimentation to demonstrate the simulation model's capabilities. The literature study included research on the following topics: the South African forestry supply chain, general supply chain theory, the fundamentals of simulation modeling, supply chain simulation as a specific branch of simulation, examples of supply chain simulation in the forestry industry, and finally, a review and comparison of different simulation software packages was done. Siemens Technomatics plant simulation was identified as the chosen software. Just to introduce you to Siemens Technomatics plant simulation, or TPS, it is a computer application developed by Siemens Product Lifecycle Management Suite. It is primarily used by individual production planners as multinational enterprises for strategic layout planning and for simulating, analyzing, visualizing, and optimizing production systems, complex processes, and material flow and logistic operations. It is one of the major products that dominate the marketplace. A large part of the time and research in the study was focused on developing process and concept model flow diagrams for the pulpwood and sawtimber supply chains. This was done by gathering information and data during various site visits, as previously mentioned, and by conducting numerous stakeholder consultation meetings. An intense iterative approach was followed to develop in-depth representations of the supply chains. This is an example of a process flow diagram, of which two were created. This one was for the pulpwood supply chain. Simon asked that I just zoom in a bit for you. So here you can see various transport options from in-field, primary transport, extended primaries, secondary, and so forth. This is an example of a concept model developed for silviculture, the silviculture part of the sawtimber supply chain. And as you can see, for the sawtimber, we also modeled standard thinning and pruning operations. This is the concept model diagram for harvesting and transport, also the sawtimber supply chain. And here you can just see that we included 5 main product types. The next part of the presentation will focus on the simulation models. The simulation models work by simulating the entire life cycle of the compartments in a plantation. It starts with a warm-up period and then simulates unestablished compartments as they move through their particular silviculture process. When the trees in a compartment have been planted and tended to, there is a large period of time when the trees just age. For pulpwood, we used 9 years, and for sawtimber, 20 years. When the compartments reach rotation age, their available yield is estimated from yield tables, and they are harvested, and the flow of wood is then simulated in 5 cubic meter batches from the plantation. When a compartment is harvested completely, it is labeled as unestablished once again, and the cycle can be repeated. This is a summary of the most important assumptions made during the development of the simulation models. So the supply chain start at Nursery Gate and end at Mill Gate. Depots are only used during rainy months. Trucks always take full loads. However, after 6 hours, if they are not full, they leave. The probability of a fire or baboon damage event occurring is a variable value chosen by the user. A single planting density and species type is assumed for both pulpwood and sawtimber. In the future, more planting densities and species can be added by the inclusion of each planting density or species unique set of yield tables. Current yield tables are for a range of site index values from 10 to 30. Operational cost, input costs, and productivity data are a combination of published research and realistic subject matter expert estimates. Now I will discuss some of the most important features that were implemented in the simulation models. These features were implemented in TPS using object-oriented programming and the embedded programming language called SimTalk. SimTalk is similar to C programming. There were many, many more features, but I will just discuss some of the cool ones. So all the silviculture operations were simulated, that is seedling from nursery, site preparation, site establishment, and tending activities. A compartment silviculture regime can be calibrated at the start of each new simulation. and specific silviculture features, for example, the interaction between fertilizer and weeding was also included. In the rare cases where fertilizer is applied but weeding is skipped, the next weeding becomes more expensive and the site index value is then reduced. In this picture, I just want to show you the buffer objects, for example, roadside, which simulates stockpiles of logs throughout the supply chain. When a compartment is harvested, the yield is extracted from a yield table by taking the compartment's site index and age into account. The calculation is also done to account for the possible reduction in yield due to fire or baboon damage. Seasonality was included by simulating both planting window and dry and wet seasons. It works by switching on or off certain activities in the supply chain based on the current season in the simulation time. The methods contain programming logic that control the interaction between objects. To further improve the simulation models, shift calendars and failure profiles were added to ensure that both planned and unplanned machine and work breaks are taken into consideration. In reality, machines often fail or are sent for maintenance and become unavailable for use, so this was considered important to simulate. The TU time is the time an unestablished compartment spends being unestablished after being harvested. It has an economic implication, and it was also included in the models. The available yield in a compartment may be reduced to up to around 40 to 100% due to fire or baboon damage. This was simulated as a random value distribution that causes a fire or baboon damage event with a probability of X on a randomly selected compartment. The input data required to develop these simulation models consisted of operational or productivity data, cost data, and other forestry-specific data like yield tables, compartment lists, and silviculture regimes. This data was either estimated by subject matter experts or taken from published forestry research, as previously mentioned. I will now briefly discuss an example of bioobjective optimization. This was done to demonstrate the simulation model's experimental capabilities. The goal of the experiment was to maximize throughput to the mill by at the same time minimizing cost by varying the number and the size of a transport fleet. Experiment 1 to 10 modeled 35-ton trucks and normal tractor trailers, while experiment 11 to 20 modeled PBS 45-ton trucks and ATL tractors. From the Pareto front, it was seen that experiment 12 had the best combination of throughput and cost. When we look at the results in terms of transport cost only, it is clear that experiment 12 is the best. It is also clear that the larger trucks and tractors cost less as they have to do less trips. In terms of throughput to the mill, experiment 12 also had a higher throughput compared to the other experiments. The conclusion of this experiment is that experiment 12 is the best option and that cost increases, fleet size increases. Throughput increases significantly if fleet size is increased from 1 to 3, but remains relatively stable thereafter, despite an increase in fleet size. This alludes to a point of diminishing return, as a larger fleet size does not necessarily correspond to a higher throughput due to the limited supply of wood from the plantation side. Lastly, for future work and model refinement, it is suggested that researchers improve the data tables for input and maintenance costs of equipment, machines, and trucks, operational costs, labor requirements, and associated productivity and costs. It is also suggested that we look further at the silvicultural regimes and the effect they have on the site index values and the predicted yield of compartments, and the interaction between fertilizer and weeding. Finally, the yield tables should be expanded to include more planting densities, species choices, and larger site index ranges. We also suggest that further supply chain optimization experiments be done with the help of forestry experts by using refined versions of these simulation models. To conclude, the research done in the study demonstrated that it is possible to use discrete event stochastic simulation models in the South African forestry industry as a tool to aid in strategic decision-making and to perform bioobjective near optimization. I just want to show you one or two extra pictures. So this was in Sabi. It's me on the left is the merchandised logs, and Prof back in me on the right, me wearing my helmet the wrong side around. This was a Jesse Vale sawmill in Malanga, and yeah, as you can see, I really enjoyed it and I learned so much, and I am so grateful for this opportunity to have experienced the forestry industry. Thank you. Any questions?